Thank you, Pratik. So, hello everyone, and so welcome to this talk. So, in this one, I will talk about two most important lattice problems, SVP and CVP, and we will see a variant of these problems in different LP norms. So, this is our main focus. So, let's first see why we want to study lattices. So the reason is lattice-based cryptography. So at least from last decade, the main reason to study lattices is lattice-based cryptography. And the first reason is lattice problems are conjectured to be secure even after quantum computers. And we also know that the security of lattice-based cryptosystems can also be based on worst-case hardness of lattice problems. So usually when we design a crypto systems, its security is based on average case hardness. But in lattices, we kind of have a reduction from average case hardness of a problem to a worst case hardness. So this is a very special property which is known only for lattices. And there are many powerful crypto primitives which are known only through lattices. And one of the example is fully homomorphic encryption. So these are the main reason to study lattices from more than a decade. And all these properties make lattice-based crypto system the most popular candidate for post-quantum cryptography. So here post-quantum cryptography means that classical crypto systems which are secure even after quantum computers. So we want the crypto systems to be run even now, but we want them to be secure even after quantum computer comes. So this is the motivation to study lattices. So in this result, we talk about reductions. So let me first motivate the kind of reduction which we look in this. So in this work, we look at exponential time reductions. And so before going to exponential time reductions, we know that polynomial time reductions are used mainly to prove the NP-Hardness of a problem. And just with respect to the hardness of a problem, even exponential time reductions are useful. And it's useful when we believe that the problem is exponentially hard and we have a reduction where the increment in the problem size is not much. So like when we have two problems and we only have a polynomial time reduction, but that reduction increases the problem size by a large polynomial factor. So in this case, in terms of fine-grained hardness, will not get much. But if we have some exponential time reductions, which does not increase the problem size, then it might be useful to give the fine-grained hardness. So let's consider a scenario. We have two problems, problem A and B. And for problem A, we know that, or we believe that there is a lower bound T. And if we can get a reduction from problem A to B, which takes time T prime, where T prime is significantly less than T, then, and this reduction also preserves the problem size, then we get this almost a similar fine-grained hardness for problem B as we know for problem A. So this is the motivation for us to study the exponential time hypothesis, exponential time reductions. And one of the other reason is if we have algorithm for one problem and it is more than the time, it is more than the reduction time, then definitely getting a algorithm for one problem will imply the algorithm for other. So now let's talk about
So I had a quick question. So
yeah.
what kind of T prime are you looking at?
So in this
T
work we are
prime
looking at
would be
2 to the epsilon times n.
okay.
Yes. So I will talk about like why in lattices they are important and how we're going to use it.
Okay.
So now let's talk about lattices. So lattice is a discrete set of points in a real space and usually specified by a basis, where basis is a set of linearly independent vectors such that the integer linear combination generates all the lattice vectors. And we use the notation n to denote the rank of the lattice, where rank means the number of vectors we have in the basis, or the minimum number of vectors we need to generate the lattice. And we use the notation M to denote the dimension, where dimension of the lattice is same as the dimension of the associated real space. So now, before talking about the lattice problems, I will define some of the notations which I will use throughout the talk. So first one is LP norms. So LP norm, like usually we study L2 norm, but we can also define the LP norm for any value of p between 1 to infinity. And for a finite value of p, it's just a pth power of the sum of the pth power of the absolute values of each coordinate, and then take the 1 by pth power of the sum. For infinity norm, it's just the maximum value of the coordinate, one of the coordinate. So now the second thing is lambda1 of the lattice. So for this one, for any lattice L and LP norm P, the LP norm denotes lambda1 denotes the minimum LP norm between any two lattice vectors. Or other way, the lattice vector which is closest to the origin, and the LP norm of that can be denoted as lambda1. So it is different for any P, and in this work we are interested for p between 1 to infinity. And the other notation is distance. So for any lattice L and the target vector T, the distance between the target vector T and L in the LP norm is the minimum distance between any lattice vector and the target vector in the LP norm. So this is so to define this lattice, we will use the notation distance between T and L. And the last notation is of LP ball. So to represent the LP ball, we are going to use a notation R times B subscript P. So R denotes the LP norm of all the vectors contained inside the ball. So as you can see, the red ball is of radius lambda1. Here lambda1 radius means that any vector whose LP norm is less than lambda1 is contained inside the ball. So these are the notations we are going to use throughout the talk. Now we are good enough to define the problem. So the first problem is shortest vector problem, and it can be defined for any approximation factor. So for gamma approximation of shortest vector problem, given a basis B of the lattice, and the problem is to find a lattice vector V such that the LP norm of the vector is at most gamma times the lambda1. So in this example, if you find any non-zero vector in the red ball, we will solve the exact shortest vector problem for when gamma is 1. And if you find any non-zero vector in the orange ball, we'll solve the two approximation of shortest vector problem. So, and the second problem is closest vector problem. And in this one, given a basis of the lattice and the target vector T, the problem is to find a lattice vector such that the distance with the LP norm between the vector and the target vector T is at most gamma times the minimum distance between T and L in LP norm. So in this example, if you find any vector within the red circle, you will solve the exact shortest vector problem. If you find any vector within the orange ball, you will solve the two approximation of the shortest vector problem. So similarly, this approximation factor we can define for any value greater than equal to 1. So now we know what is SVP and CVP. So let's talk about the state of art for the approximation of SVP and CVP. So for the up to the approximation of m to the power 1 by log m, the SVP and CVP is known to be hard. And please note that m denotes the dimension of the lattice, and when the approximation factor is square root m or square root m by log m, we believe that it is not, and it is not hard because it is in the for square root m it is in the class np intersection co-np, and for square root m by log m it is in the class np intersection co-m. But for us, the interesting reason is when the approximation factor is poly in the dimension. And mostly in cryptography, when we use lattices, or all the lattice-based crypto system security is based on polynomial approximation of SVP and CVP. And with respect to the polynomial time algorithms, the best approximation factor which we can achieve is 2 to the power m times log m by log m. So this is all we know about approximation of SVP and CVP in different LP norms. So now let's move to reduction between the lattice problems. And so before talking about exponential time reduction, let's see what we know in polynomial time reductions. So from reduction from CVPp to SVPp, so in this one we are preserving the norm. There is a reduction norm which also preserves the approximation factor, dimension, and rank of the lattice. And this reduction came in 1909 by Goldrich, Michancio, Safra, and Seifert. And in other direction, there is a reduction norm only for the L2 norm, but in this reduction, we lose at least square root m approximation factor. And this reduction goes from square root gamma square times square root m approximation of CVP in L2 norm to gamma approximation of SVP in L2 norm. So this is all we know about reduction between CVP and SVP. Now let's talk about the reduction between CVP in different LP norm and SVP in different LP norm. So a trivial reduction between SVPp and SVPq increases the approximation factor by m to the power 1 by p minus 1 by q. Here this approximation factor comes trivially by the relation between the LP norms. And a similar reduction we can also show for CVP. And so there was nothing much known for reductions between these problems in different LP norm till Regev and Roshan came up with the idea of norm embedding, and they gave a reduction from C times gamma approximation of SVP2 to gamma approximation of SVP in any LP norm. And here C is a constant, but this reduction does not preserve the dimension. And at least when p is greater than 2, there is a super constant increment in the dimension. And this reduction only goes from L2 norm to any LP norm. So this reduction also kind of implies that that L2 norm is the easiest problem, which is L2 norm is the easiest for CVP and SVP. So now let's move to algorithms for SVP and CVP. And the reason I'm talking about algorithms here is before going into exponential time reductions, we want to know that what is best time complexity norm for SVP and CVP and what we can hope. So the most of the progress in the algorithms is for L2 norm for SVP, and we know that for any approximation from 1 to polynomial in M, algorithms takes 2 to the constant times M, where this constant depends on the gamma, and which is less than 1, but it is significantly or at least greater than 0.1. Okay. And for gamma approximation of CVP, we know that it takes exponential time. Similarly, for constant approximation of SVPp, the point to note here is when p is not equal to 2, the constant c is not well studied. So there is no upper bound known on the c. So we don't know whether it can be solved in 2 to the n time, or we need 2 to the 100 n or 2 to the 100 m. So So there is no upper bound known, but in terms of lower bound, recently there has been a series of work by Agarwal, Bennett, Golovnev, and Stefan Davidovits, and in this one they show 2 to the power 1 minus epsilon n lower bound for small constant approximation of CVP in any LP norm and SVP in infinity norm. And these lower bounds come by assuming strong exponential time hypothesis and their variants. So we believe that at least for any LP norm solving CVP and SVP infinity is not possible better than 2 to the n time. So assuming that we can't solve lattice problems in better than exponential time, it's good to talk about exponential time reductions. And so there has been some work in exponential time reductions, and the first work in this direction was by Aitai Kumar and Shiva Kumar. They gave 2 to the big of m reduction from constant approximation of CVP in L2 norm to a variant of SVP, and the variant is to almost uniformly sample lattice vectors within a sphere. And even for this reduction, we don't know what's the constant in the exponent here, and they use this reduction to give a algorithm for CVP by using a algorithm for SVP. And later this reduction is generalized to LP norm. And recently there is a work by Eisenbrand and Wenjin. They gave an algorithm for constant approximation of SVP and CVP in any LP norm by using constant approximation of SVP in L2 norm. So this why I'm saying this is algorithm, because their reduction uses some specific property of the current fastest algorithm for constant approximation of SVP2. So before this, it was believed that for when p is not equal to 2, the lattice problems are hard. But because of this reduction, we know that the most of the progress is in the L2 norm, and now the similar algorithms, the time complexity algorithms are known for CVP and SVP in any LP norm. So now let's talk about our contribution. And so in this work, we show a number of reductions between SVP and CVP, and which takes 2 to the epsilon m time. So first reduction is from SVPq to SVPp, and we lose the approximation factor by order of 1 over epsilon to the power 1 by p. And it is like we are reducing SVP from a larger norm to SVP in a smaller norm. And similarly, we have a reduction from CVP to CVP, but from a smaller norm to a larger norm. And the loss in the approximation factor is same. And then we have a reduction from CVP from a larger norm to SVP in a smaller norm. And the loss in approximation factor in third reduction is high, which is 1 over epsilon to the power 1 plus 1 by p. And we can also have a reduction from CVP in smaller norm to SVP in a larger norm, like by using the reduction 3 and 2. So by using a reduction 3, we can have a reduction between CVP to CVP to SVP in the same norm, and then by using the reduction first, we can go to the smaller norm. So these are the set of reductions which we have, and the main property all this reduction has is they preserves the rank and dimension or increase them by at most 1. And yes, 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 Yeah, so for reduction 3, we can also we can interchange P and Q by using the combination of all these reductions. Okay, so this is the pictorial view of all our reductions. So the solid line represents our contribution, which is 2 to the epsilon m time reductions, and the dotted line represents the polynomial time reduction by Goldrich, Michancio, Safra, and Seifert. And so there are still open problems, as you can see, from SVPp to SVPq, and similarly also from CVP to CVP. And when we reduce CVP to SVP, we get a slightly stronger result. If we reduce CVP to a variant of SVP, which is gamma, which is unique SVP problem, which is known to be easier, which is known to be easier than the SVP. So this is the first set of result, and for when p is between 1 and 2, we get slightly better result. So uh, for reduction from CVPp to SVPp, we get 2 to the epsilon m time reductions, but the loss in the approximation factor is only 1 over epsilon to the power 1 by p. And as a consequence of this result, when we put p equal to 2 and epsilon equal to log m by m, we get a polynomial time reductions from square root m by log m approximation of CVP in L2 norm to exact SVP2. So this is an improvement over a Kannan's celebrated result, polynomial time reduction from square root of m approximation of CVP in L2 norm to SVP in L2 norm. And this result is way different than the original reduction given by Kannan. So this is all about our contribution. So in rest of the talk, I will discuss at least a variant of our third reduction, which is from CVP in larger norm to SVP in smaller norm. So now let's talk about this reduction. So in this reduction, we start from a already known idea of Kannan's embedding.
Sorry, I had a
Yes,
quick question. So, going from SVP small to large, is
SVP
the
small.
reduction only the loss in approximation is the only known thing, which is like the trivial one due to the
Yes, yes.
norm change, or is there anything better known?
Nothing. So this is the first
Okay,
time we are studying the reductions between the different LP norms.
okay,
So
okay,
before this, there is only one reduction known, which by Regev and Roshan, which is from L2 norm to any LP norm.
okay.
So, so, so we start with Kannan's embedding. So, so we want to use SVP oracle to solve the CVP problem, and the idea is to find the closest vector to a small integer multiple of t. So how we do it? So let's assume b prime as the new basis of lattice L prime, where b is the original basis of lattice L, and t is the target vector, and s is some constant which we'll use which we'll choose. So if we see the shortest vector of the lattice L prime, it is of the first m coordinates are of form v plus k times the target vector t, and the last coordinate is k times s for some constant k. And the idea is to solve CVP by using SVP here is to make sure that the shortest vector is when k is equal to 1. So choose s appropriately such that when k is equal to 1, you get the shortest vector. So when so this is the idea known from a long time, and almost all the reductions or all the algorithms which comes from SVP uses this thing. And recently Eisenbrand and Vengeance observed that it suffices to simultaneously find two lattice vectors. One is close to k times t and one is close to k minus 1 times t. So if we have two two such lattice vectors, and if we subtract them, then their subtraction is closer to the target vector t. So here is like, so if you get two vectors, one is of form v plus k times t, and the other is some v prime plus k plus 1 times t. And if we subtract them, then we get a we get a closed vector to t. So this is the idea of Kannan's embedding, and this is the reason why we say that the dimension and rank increases by 1. As you can see that there is an extra row and column added, just to extra column for t and s, and extra row for 0 and s. So in this reduction, we are given a basis b and the target vector t. We construct a new basis b prime, and with carefully chosen value of s, we sample two short lattice vector from the lattice L prime, and we check if the difference of the two vectors is of form y plus t comma s, and also their norm is small. If we get the vector of such kind, then we terminate, otherwise we repeat. So this is a very simple reduction, but to show the correctness of this result, there are two things we need to show. First one is how to sample short lattice vector by using SVP oracle, and the second is to prove that if we repeat this algorithm 2 to the epsilon m time, then with high probability we'll get the closest vector or one of the closed vector. So first was sampling the lattice vector uniformly by using the SVP. So this is also a known technique of lattice sparsification, which is due to Subhash code. So the idea here is, for a prime p and a uniformly random vectors z, consider the lattice L prime z, where it contains all the lattice vectors such that the dot product of z and b inverse v is 0 mod p. So we know that this L prime z is also a lattice, because if it contains two vectors whose dot product is 0 with z, then even for their summation the dot product is 0. So this is the sublattice of the lattice L, and the main observation here is, if the probability of any vector v which is in the lattice L to be in the sublattice L prime z, the probability is almost 1 by p. So there is a small factor of order 1 by p square, but that is small, so we can ignore it. So the probability is almost uniform for a vector to be in the new sublattice. So for a uniformly random z, if we consider the lattice L prime z, then it's a new sublattice of lattice L, but it is more sparsified compared to the original lattice. And so by using this observation, Noah, Stephens, Davidovich show that if we make a polynomial number of calls to SVP2 oracle, then we can sample uniformly random lattice vector in a sphere. So sphere can be of any radius, and if we have exact SVP2 oracle, then by making polynomial number of queries, we can sample a uniformly random lattice vector. And in this work, we use a generalization of this result to any LP norm. And here we want to sample a uniformly random lattice vector in a LP ball. So by using this technique, we are able to do it. So now the sketch of this proof is, so first we show that there exist two spheres S1 and S2, and there is a difference between the radius of these two spheres. And the first condition we want is the number of vectors in S1 is not much smaller than S2. So we know that the number of vectors in S2 is at most 2 to the epsilon m times the number of vectors in S1. And then we show that there exists a set S in sphere S1 on one of the hyperplane, and the number of vectors in set S is also not very small compared to the size of the number of vectors in sphere S2. And then we show that for the set S, we can also find a set T, and these two sets are from a conjugative hyperplanes. And if we can get one vector from set S and one vector from set T, then the difference is a good enough solution for closest vector problem. And we know that we can uniformly sample the vector from the sphere S2. So if we know that the set S is not much smaller than S2, then with 2 to the power minus epsilon m probability, we can find a vector in set S. And similarly, with 2 to the power minus epsilon m probability, we can find a vector from set T. And so by repeating this algorithm 2 to the 2 epsilon m time, we can say that we'll get one vector from S and one vector from T, and the difference is the solution for closest vector problem. So this is it for proof sketch of our reduction. So to conclude, so in this work, we gave a number of reductions between the lattice problems in different LP norms. And as a corollary of one of our result, we get a better polynomial time reduction from square root m by log m approximation of CVP in L2 norm to SVP in L2 norm. And the importance of this result come in a scenario that before this work, we used to think that there are few LP norm for which the lattice problems are hard, and there are few LP norms for these problems are way easier. And it would have been possible that in future someone would have come with algorithm for a specific norm, and it's hard to define the same algorithm for the other norms. And it happened. So in past, all the algorithmic techniques are same, but for different LP norms, we were getting different bounds. But due to this result, now any improvement in the algorithm for one problem will imply the algorithm for other problem. And there is one more consequence of these results is the heuristic algorithm. So for lattice problems, so at least for SVP and L2 norm, there is a long line of work for heuristic algorithm, and which is not done for any other lattice problems. So due to these reductions, the similar heuristic algorithm we can also assume for all the other lattice problems. So this is it. Thank you all. And if you have any questions. Anything in proof sketch?
So why doesn't this work for going from smaller norms to larger ones for SVP? Like where?
So for that, the issue comes is so there is a so if we so for so there are two different ideas which we use. So the main limitation comes, we can only show that if we have a LP ball by, so suppose we are given a LP ball and we want to bound the number of LP balls of LQ balls of radius r such that we can cover a LP ball. So this reduction is known when we are covering the smaller norm ball by a larger norm. So in other direction, it's not known, or I think it's just a just a technical view. Otherwise, it should work. Like we are also trying, and I don't think it will be much difficult. Like just just a calculation point of view, we are just stuck.
Mhm. Okay.
Mhm. No, no, no. All are randomized. Most, hmm. Mm, so there is not much improvement. So there is a slight improvement in the constraints, but not much. Like, like whatever constant we are assuming in the exponent for classical, you can say at most. So for quantum, we'll have at least c by 2, like just a half improvement in the constant, nothing much. Yeah. Okay. Thank you.